Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss using Newton's method for finding extrema in n dimensions. So in this topic we will be describing how to use Newton's method to find extrema for real valued functions of a vector variable. We'll reintroduce the concept of the gradient and the idea of the Jacobian of a vector valued function of a vector variable. Specifically, we will be using or applying the Jacobian on the gradient to create a matrix called the Hessian. We will look at two examples and see how quickly this actually does converge, and then we will try to understand when to use this technique and why. Now, the idea for finding an extrema of a real valued function of a vector variable is very straightforward. We're simply going to apply Newton's method to the gradient. And you'll recall that the gradient of a real valued function of a vector variable is a vector valued function of a vector variable. Now, the issue we're going to see is that we will not be sure if the point is a maximum, a minimum, or a saddle point. This is exactly the same problem that arises when we are dealing with using Newton's method to find an extrema of a real valued function of a real variable by applying Newton's method to the derivative. And recall, a saddle point is any point where all the partial derivatives are zero, but where the function does not achieve an extremum. Now, at an extreme point, all the partial derivatives are zero. If you're at the top of a hill, then it doesn't matter which direction you're going to go in, you're going to be going perpendicular or parallel to the surface of the Earth. Consequently, we must find a point such that the gradient is equal to zero. That is, all the partials are zero. Now, you'll recall that the gradient of a real valued function of a vector variable is simply the vector of the n partial derivatives of f. Thus, the gradient of f equated to zero becomes a system of n equations in n unknowns. Now, if f is a constant function, then of course every point is an extrema. If f is a non-constant linear polynomial in U, then there are no solutions, for the gradient is a constant non-zero vector. If f is a quadratic polynomial in U, then the gradient defines a system of linear equations. Well, in this case, we don't even need Newton's method. We can just use linear algebra. In all other cases, the gradient is going to be a nonlinear function, so we can just go right on back to Newton's method in n dimensions. Basically, recall that Newton's method in n dimensions, we find a solution to a vector valued function of a vector variable g by choosing an initial guess u sub naught and iterating by solving the Jacobian of g evaluated at u sub k times an unknown delta u sub k equaling negative g evaluated at u sub k. Solving for delta u sub k, the next approximation is simply the previous approximation plus delta u sub k. Now, in this case, our vector valued function of a vector variable is the gradient of f. So basically what we're doing here is we are solving the Jacobian of the gradient times an unknown delta u equaling negative the gradient at that point. Having solved for delta u sub k, our next approximation will be the previous approximation plus this delta. Now, the Jacobian of the gradient of a real valued function of a vector variable is called the Hessian. of that function. And there are different notations. However, we will continue to use the notation with the Jacobian. And again, because the result is a matrix in this course, we always represent the function name by a bold capital letter. Now, if the function is sufficiently differentiable, the Hessian will be symmetric. And you will recall from linear algebra that if you have a symmetric matrix, the eigenvalues must be real. That will be useful later on. Now, this is the Hessian of the function f. You will recall that the gradient is just a vector of the partial derivatives. You will recall then that the Jacobian simply took the first entry, which in this case happens to be the partial with respect to u1, and took the partial of that entry with respect to each of the n variables. So as you can see, that first row of the Hessian is the second partial with respect to u1, then the partial with respect to u2 of the partial with respect to u1 of f, all the way up to the partial with respect to n of the partial with respect to u1 of f. And that is the same for each of the rows. So really, this is simply the definition of the Jacobian, but now it's applied to a vector of partial derivatives. So essentially it becomes a matrix of second partials. Recall from applying Newton's method to the derivative of a real valued function of a real variable, we saw that a solution to the derivative equaling 0 is a local minimum if the second derivative at that point is greater than 0. It's concave up at that point. It's a local maximum if the second derivative is less than 0. It's concave down at that point. And it's of unknown character if the second derivative is equal to 0. It could be a maximum, it could be a minimum, or it could also be a saddle point. Well, the same applies for functions of a vector variable. A solution to the gradient equaling 0 is a local minimum if the Hessian is positive definite. That is, if all of the eigenvalues of the Hessian matrix are positive, greater than 0, then we're guaranteed it's a local minimum. Because essentially we are guaranteed we have concavity up in all directions. It's a local maximum if the Hessian is negative definite. That is, all of the eigenvalues are strictly negative, less than 0. What that means again is that in all directions we are concave down, so it must be a local maximum. And it's of unknown character otherwise. Well, more or less. Of course, if you have both positive and negative eigenvalues, then it's guaranteed to be a saddle point. But if all of the eigenvalues are greater than or equal to 0 or less than or equal to 0, we don't know. Now, consider this function of 3 variables. Rather than using u sub 1, u sub 2, and u sub 3, I'm going to use x, y, and z because it's simply clearer to see. However, from a programmatic point of view, it's better to always think of a multivariate function as a function of a vector variable. Consequently, we can see that this is a quadratic polynomial in the entries of u, and therefore you will notice that the gradient is actually a system of linear equations. Consequently, the Jacobian on the right-hand side is a constant matrix. So, in the special case that it's a quadratic polynomial in u, we don't even have to apply Newton's method. We simply have to solve a system of linear equations. And the easiest to get this is to solve for the Jacobian evaluated at 0 equaling the negation of the gradient evaluated at 0, and that gives us that expression there. We solve that, and thus u, the solution, is 3, -1, 0. If you were to substitute 3, -1, 0 into the gradient, you would find that all of the entries are 0, and you would find that f evaluated at this point is -44. You will notice that the matrix, or the Jacobian, is strictly diagonally dominant. It's also symmetric. Therefore, not only are all the eigenvalues real, but all the eigenvalues are guaranteed to be greater than 0. Consequently, that matrix is positive definite, and we are guaranteed that this solution is a local minimum. Now, recall that if you applied Newton's method to a system of linear equations, it would converge after only one iteration. That's useful because what that means is you don't really need to check if the gradient equated to 0 defines a system of linear equations. You can just start at any point, and after one iteration, you are guaranteed that you are at a place that satisfies the gradient equaling 0. All right, let's consider a function that is going to give a gradient that is nonlinear. And this is definitely a function that is not going to give you a linear result. So here is a plot of this function in two variables. Once again, just to be able to distinguish the two variables, I will use x and y, but we will assume that x and y are the two entries of a two-dimensional vector u. And here is a plot of that function over a region. Now, if you take a look more closely, you will find that there appears to be a minimum close to the point x equals -0.2 and y equals 1.8. So let us use that as our initial value, and let's see if we can use Newton's method to converge to the actual extreme point. So, given this particular function, we can calculate the gradient and the Hessian. So here's the gradient, the partial with respect to the first variable, in this case x, and the partial with respect to the second variable y. We can then calculate the Hessian, or the Jacobian, of that. So we take the first entry of the gradient, and we take the partial with respect to x first, and then we take the partial with respect to that first entry with respect to y. That becomes the entry 1, 2. Then we do the same with the second entry of the gradient. We take the partial with respect to x, and then the partial with respect to y. Now, let's start with that initial guess, -0.2, 1.8. And we can evaluate the function at this point and see that it's approximately -2.92 and change. We can evaluate the gradient at this point, and we can evaluate the Jacobian at this point. Thus, we would solve this Jacobian times delta u naught equaling the negation of the gradient, and that is something we can do in Matlab or using any other package, and we get that delta u naught is this vector we see here. Thus, our next approximation is assigned the current approximation u naught plus this delta u naught which we just found, and that gives us this new vector which is close to, but not exactly, well, in the vicinity of our initial vector. And if we evaluate f at this new vector, we get negative 2.931 instead of negative 2.924. So again, we seem to be moving towards a minimum. Continuing, we can take this point and there's the value that we just calculated, and we can calculate the gradient at this point and the Jacobian. We can solve the Jacobian times delta x1 equaling the negation of the gradient, and that yields this delta u1. And notice we have approximately twice as many zeros. Recall that Newton's method is order h squared. So we can now set our second approximation u2 to be u1 plus this delta, and that gives us this point here, and we get that f evaluated at this point is once again slightly smaller. Not much, it's actually only smaller in the last three digits, which are 404 versus 865, and since it's negative, this one is now more negative than our previous one. So we seem to be really, really close to the minimum. My apologies. Finally, with u2, we can have that point. We have the function evaluated at it, and we can once again evaluate the determinant, the gradient at that point, and we can also find the Jacobian at that point. You'll notice the Jacobian hasn't changed much. We can solve this system of linear equations. This gives us delta x2, and u3 becomes u2 plus this delta, and we notice that, the value of the function hasn't changed, at least to 10 digits after the decimal point, and so we seem to be really close to the solution. You will also notice that the Jacobian, or the Hessian, at this point is symmetric, but also strictly positive definite. Therefore, all of the eigenvalues are strictly greater than 0, and therefore this is guaranteed to be a local minimum. Now, the images were made, and the results that we just saw were all verified in Maple. However, the Matlab code for the previous example was as follows. I defined f to be a function that takes u and maps it onto the expression. I then calculated the partials with respect to u1 and u2, and that gives me the gradient, so I defined a function that returns a vector. And here's the Hessian. And the Hessian is, again, just the partial derivatives, which again I used Maple for. Then here's my initial approximation, and I just did 4 iterations for fun. By not including the semicolon, the first statement simply prints the value of f evaluated at u. This prints the gradient evaluated at u. This prints the Hessian evaluated at u. And now we solve for the delta. And our next approximation is the current approximation plus this delta. And we're just going to overwrite u and use it again. Now, when to use this technique? Well, suppose you're simulating a system that you've modeled. Well, chances are in your model, you have mathematical descriptions of each of the components of your system. Consequently, you should therefore be able to explicitly calculate both the gradient and the Hessian exactly. On the other hand, if you have a black box function f for which you cannot compute the partial derivatives, you can only pass data in, get a value out. In that case, you can at best approximate the gradient and the Hessian, and therefore other techniques are preferable. Following this topic, you are now aware that Newton's method can be used to find extrema even for real valued functions of vector variables. You understand, to do this, you must be able to compute both the gradient and the Jacobian of the gradient, that is, the Hessian. You understand that other techniques, however, are preferable if you cannot explicitly calculate the partial derivatives. Finally, you saw two examples. In the one case where it was a quadratic, then actually only one step was required. However, in the second case, a number of steps very quickly brought us to the solution. And if you noticed, you also saw that the rate of the convergence was order h squared. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!